Okay, so J.C. Johnson brought me into this deal. I'm very grateful he did, because this is an amazing research area with all just unlimited potential, it seems like, with what's happened to us so far. He knows that I was doing some research over on another bosky region here in New Mexico, very similar situation to this, in which we've had quite a bit of success, and called me to see if I could come down and do some serious study work, recon, and evidence collection work a little above and beyond, and see what we could get for the study he's got going now, where they've got several different contributors all the way from the Chusca Mountains all the way down here on the San Juan riverbed. And where I'm at is a very similar situation. It's on the Galisteo River basin. Again, there's people all over the place, kind of the same deal. They're in a thick bosky region, feeding high on Russian olive all winter long, and we've done our studies in the winter, mostly once the temperature drops below 20 degrees at night. And the reason is because we can eliminate most of the human activity, if not all the human activity, in and around the river systems, because nobody's walking around when it's 20 and less, 10 degrees below freezing. I want to reset you. Okay. So the point is that no one's going to be running around out here when it's 10 degrees below freezing at 20 degrees, middle of the night, walking their kids through the river systems. So what we get to, I want to show you some of the evidence that we've collected on the other river system and how this kind of works out. Our first thing we're going to be showing you is a contribution. Excuse the wind. Welcome to New Mexico. Yeah. So our contribution to this study is going to be this hair sample, which came from the Galisteo River Basin, which should be from an adolescent individual or a junior. It's orangutan orange. It's a short, fine strand without really any visible guard hair or undercoat. So we believe it came from the forearm, also based on the collection position. Just 28 inches off the ground on a downward facing stick, where I had been studying something had been killing birds, plucking the birds and piling the feathers in perfect little piles. And of course, it was very much like this behind me, where they had tunnels hewed out through these regions, but some of them are totally cleaned on the bottom, the ones they occupy more than others. Well, this animal had been taking birds into these tunnel systems up a clay bank, where anything with normally a bear, mountain lion, coyote, anything's going to mark the ground and leave plenty of marks trying to get up in the clay bank. I had gone in there and then gone back 24 hours later, and when I went in there, this was not present. 24 hours later, this was. So it had entered there after I did, directly following, gave us a chance to make this collection. So that was accompanied also with tracks, with scat material, with the bird kill sites and pluck sites, and the hair all came together. Some of the other evidence, and I'll give you. So we studied this family for about 2 years down there, and we noticed that they had a baby, and in the fecal material, a lot of it was blue from lactating. So the infant, we knew at least one of the babies that they had was lactating, but the feet we were finding associated with it was about 7 inches long. And I thought, well, wow, they're really breastfeeding these kids up into the 2s and 3s year old. And because the scat we had found was plain and simple, you know. I didn't realize until later, when we actually found evidence of a smaller individual, that the junior, or who we call Amos now, he was there the entire time, showing marks, showing tracks, but he wasn't the one being breastfed. And you don't get very many chances, but every once in a while, Mom will put them both down. By the time we discovered the second young one, Amos's foot had grown to 9.5 inches from 7.25 inches. This is Amos. And it may look very human to you, except in the camera you'll probably see a lot of indications of strange line patterns in the foot. These are the macrodermal pattern to the foot. And this pattern is all based around a circular structure here. And you can, I'm sure, see the arcs to that circular structure as I turn it around in the light. You'll see we have these deep, deep gouging lines in the foot, and they all run kind of around a circle here. Well, that's consistent in all the hominid tracks that we've worked on, but not any human foot we've ever worked on. I thought this was the baby, like I said, until we saw this one's prints, which none of them cast very well, but the handprint cast really, really well. And what you've got here is the palm and knuckles of a right hand, and it's this guy's little brother. And at this point, he was still a knuckle dragger. So Amos was walking, holding the hand of the young'un, and the other hand he was using to assist himself along with. Then we realized, wow, they've got two little kids in the group. Distance foot being 5 1/4 inch. At this point, Amos is already over 9 1/2. Now, because they have kids down there and such, Amos isn't old enough, I guess, to be in charge of watching the other little guy. So in charge of that was one we called George. George was chasing this little guy around quite frequently. And when he learned to walk, which was about 4 months after this cast was taken, he was off his knuckles and he was up and walking. Already like a 3-foot step gap, which is way too long for his size. And at one point, he had run directly out of a thicket, worse than this, full of Russian olive, which these all contain 2-inch thorns. If I take this off, it may look awful nice, but on each one of these is a thorn, and they go up to 2 inches long. You can see here. That's absolutely unforgiving. You'll cripple a human being with that. Well, little Junior here, the infant, now its foot's about 6 inches long, which the big toe makes up a great majority of the foot on, which is very comical. Comes tearing out of a thicket of these kind of thorns, and by the tracks we see that he comes tearing directly out of a thicket at 90 degrees to the riverbed and out into the mud. Just like any other little kid, once they learn to run around, they'll just run like banshees. Well, running like banshees, they're not really allowed to do that. George is the babysitter. So George, who normally never leaves any viable sign, is forced to have to step in the mud to go get back the little guy. So he does. He goes down the rock mass, he takes 2 steps out, snatches the little guy, so the prints stop in the middle of nowhere, snatches him straight up. And on his way back, he left these. And what this is there's a 1 foot out, and the other foot came back in the same placement. And so if we put these together, he stepped right over his own step. Now these have complete dermal patterns, macro and microdermal ridging, abrasions, cuts, and damage. Most of what you see here is the actual surface of the pad of the foot. There is some deviation, like this was a mullein leaf and a split in the ground. These were bubbles. But other than that, these big holes in the pad and this multi-surfacing to the pad, which you can see lines, and if I turn it, you can see microdermal, or the microdermal ridges, and then the macrodermal pattern is also visible if you start just catching the system of lines here. He also has a large scar on the foot right here, which is a little difficult to see, but you can see the dividing lines come across, which would be right there, right there, right there, and it makes a circular feature here that even has scar tissue and lines all the way out around it. So at one point or another, it's had quite a bit of foot damage right there. Now this is George, so like I said, he had to step out to grab the infant out of a position he never would have normally showed himself. Now people see this deep arch, and they think, well, that's not a Bigfoot. A Bigfoot does not have a solid or fused foot. And we can see that through many, many examples, one of them being Amos's print. This is his little brother. In his little brother's print, it's the identical same morphology, or the mathematical ratios to the bone structure of the foot are identical, but they would be unlike any normal human, except maybe a really wild fluke. And what we'll show you or what I've got here to show you to demonstrate this, is we go to the back of the first metatarsal and to the front of the fifth. And from those 2 points is the hinge point of the foot, or what most researchers would call the center break, or the margin in the foot that's able to hinge. Well, they actually have 2 of these margins, and one's at the front and one's at the back. And that's just because of the bone structure of the foot. Our bones are longer in the center, it causes a fused arch, which doesn't do anything. They, on the other hand, their foot is just like our hand. So it can be arched, it can be flat, it can be arched to an anterior, posterior, anterior as well, just as much. Their foot will articulate in either direction. The reason for that is the extreme weight and the way this hinge point has to place full weight and then full weight on the triangle to run. So we end up with full weight on a triangle here to receive and then full weight on a smaller triangle to transition the weight off. We don't do that. So if I lay this block down on Amos's foot, you'll see that it hits these 3 points. And it hits the exact center of the heel, and it's equal to the foot. So the foot hinges in a direct forward manner. The human foot is cantered off about 30 degrees. And that's because of our hip structure and the way we walk. We walk like this with our feet separated. They cannot do that. Their feet walk in line. And the reason is that is because the hinge is directly forward. Foot over foot over foot. That's because they can't sway their body weight once they get to a certain size. They're just too big and heavy to sway 2,000 pounds. It takes 6,000 pounds of force to stop the sway. Same with the undulation. This allows for the foot to be fully planted at any location. All the weight can be put on the heel, or all the weight can be put on the front of the foot based on the material which they're standing on and how they want to transfer that weight. You can see the raised tendon across here, and you'll see the same raised tendon here, and a larger feature off the fifth metatarsal. This fifth metatarsal also is greatly exaggerated above any other normal human. As well, you'll notice the ratio of the length of the big toe and first metatarsal are greatly exaggerated in the length of the foot to a human. This is more so when they're younger. This toe structure is huge. Even when the foot is much shorter, it'll almost make up half of the foot. You'll see that by the time Amos gets to this size, the overall toe structure has not changed much. The toe position, first metatarsal, they're not much different, even though the foot size is tremendously different. So this toe structure is greatly exaggerated in the young ones because they're going to grow into it as they mature, and they grow very, very fast. Now what really clinched all this was another print that we had retrieved that I did not understand the morphology on at first. This one's about 40 miles away from these guys. And this is a 22-inch print with most of the print missing. And if I would have known more about these prints, I would have understood that at this time that the toe would have been here, because I saw 2 large divots about this far up the foot. And I thought they were a hand print, thought it was a double print. So I cast short. Now realizing what was really going on here is it looks a little strange until you compare it with either of these. And we've got her for reference, we've got some marks on the foot here. You'll take note of these marks. This bone in this foot is protruding here. This really hard, you'll see all 3 of these, the front of the fifth metatarsal is where it connects is huge and robust. This entire feature is, and extremely well defined, as is huge and robust and extremely well defined on this print. The little toe is up a little bit, which is this toe. And as you can see here, it curves up and sits over this toe. Little toe curves up, sits over this toe. Little toe curves up, sits over this toe. Now finally realizing, I thought this was the bone to the back of the first metatarsal. Realizing that this is this bone and that bone and this bone and that bone made me realize that the entire large or great toe structure is displaced. It's deflected. So what it is it can either be down or it can be up, and do just like my thumb does. This entire structure will raise and lower, offering a big division line. This division line in this circle and depression is matched with the division line and circle and depression in this foot. George's pads are way too robust to be able to see those structures. Of course, you can see the depth of the pad as well here. So what human has a pad that's over an inch thick before his toes come out? You can see where the normal foot would be here, toes are here, the pad's close to an inch thick. That's from having to live the way the big males live, because they travel, they move. This is an older individual, about 12 feet tall, gray hair, cooperative hunts with females because he's very old. He hasn't got the robust nature to the foot anymore. He's a very old individual. Amos's was made in the wintertime, so it's a little bit deflated. We also notice here is we have a macrodermal pattern that's the same macrodermal pattern as the other feet. We have an inner circle here, which you might be able to make out, and then we have a little outer circle and ribbing that come around this side. Most of this was decomposed granite, so it did not take a very good cast. But what we do see is first tendon here behind the major bone, tendon here, major bone. This tendon is there, but it's deflected. Then we have the tendon off the fifth metatarsal crossing the foot to the center, tendon off fifth metatarsal crossing the foot to the center, tendon off fifth metatarsal crossing the foot to the center. In all three, there's a bump here, and a bump here, where that attachment takes place because of the flex. It's so exaggerated. Something else I'll go ahead and run down is the scat material from the Piedralisa individual over the mountain. This was collected at 10,000 foot elevation, mid-December, on top of frozen snow, where he just cleared a big area and ate a bunch of pinon. Now, this is comprised 100% of pinon shell fragments that have been chewed up by something with molars. It wasn't a bear, it wasn't anything with a canine structure or scissor teeth. And whatever it was capable of harvesting only pinon shells, nothing but pinon shells, which takes great dexterity in the woods to just pick that up and get nothing else. So he's not picking it up with the mouth, or they would inadvertently get small organic material, they would get minerals, dirt, rocks, small bits of pine needle, other forest refuse that is too small to get off the shells. Picking up with the mouth, you're going to get that. This contains nothing. If it was bear, it would also have insect fragments, grub fragments, vegetable matter fragments, and all this. Nothing. Solid pinon. Now, besides just the time of year that it's taken and all that stuff, is that no other animals can really forage for the pinon because it's buried in the snow. You have to first clean the snow and then pick them out. A bear's not going to be up there in mid-December. Also, this scat, this represents about 1/3 of the diameter, a sliced pie about 1/3. So the scat itself would have been about that big around in diameter, and it was over 14 inches long. If it was a bear, it would have had to have been a massive grizzly bear, a massive Kodiak bear, or something like that to have done that. No black bear in the world gets big enough to have defecated this mass. It would also, it indicates and infers that about 15 pounds of pinon were eaten in a single feeding to get this many shell fragments. Not many animals can eat 15 pounds of pignuts in a single feeding anyway, without extreme intestinal distress, because it's all sharp, jagged nuts and fragments. This piece, of course, has been plasticized. We also have a couple other, these are also other types of scat material from hominids. This one's almost loaded in deer fur, and it shows that, and meat proteins. And what that shows you is this is part of the meat part of the diet. This is an example where that would be the nuts. And then they also eat algae. They almost survive on Russian olive, which we could go and actually show some Russian olive scat material. So in the wintertime, they move their families down into these river basins, and they just gorge on Russian olive because it's pure carbs. And if I just turn around, probably right in here somewhere, I'm going to find Russian olive all scattered throughout all of this material. This is a specialty food here, and what this is beetle dust and some other seed shells and hulls from pine nuts that are not pinon, regular pine nuts. This animal had been eating, and this is outside through by Blue Lake, in a dry pine forest, and had been eating yucca and biting, pulling leaf by leaf, biting the end off, leaving a bite imprint in every one. Thousands of examples. And what I thought was more interesting was that it had been cleaning out the beetle dust out of the dead trees. And apparently, based on the scat, it had been eating the beetle dust, not just the grubs itself. So apparently, after the pine has been digested by the grub, it becomes a food source. So that's about it for us today. We've also found today the prints we find in here are fitting the same morphology, the same type of shape, styling. Sometimes the toes are splayed, sometimes they're arched, sometimes they're not. But it is interesting that from what we've learned at the GLST research area, where most of this came from, this being not the case, we see certain forms of scat where the entire family will go defecate together, within a foot or 3 feet of the water's edge. And if that's not convenient or it's too open, they'll pick a place behind a thick bosque or a thick tree or foliage area that's open and protected, that's not going to interfere with where they go or their food source or anything else, and they'll all defecate there. No, just learning what we've learned here gave me the ability to come into this region on the San Juan, and we made a couple predictive finds, which is where the scat would be located. The first stop we did, we found 2 scat piles within a foot of the water. Interesting component being is that there was a little what was scat, but it started out to be plant protein or algae, and it was deposited along with the toddler, meaning an infant was present. So the predictive nature of the results we've had here were started and formulated at the GLST site, which gives great validity in the second time we've seen all the same parameters with the individuals, even right down to habits and how they're treating their kids. So if it's a fluke in one location, then we wouldn't have predicted results at this location. And those are everything from hair to the scat, to the feet print, to the activity, to even having the rocks thrown at us. All these things are activity and action and habits of the animal we've been able to discern over a 3-year study, and it's just showing true here as well. So we drive 200 miles away. We have absolutely identical results that we have at our former research site.